GLC, Gas-Liquid Chromatography. Now this is one of those videos where I think you might need to get your pen out and make some notes, maybe. Do it perhaps alongside textbook as well. GLC, type of chromatography, standard chromatography from when you were small, paper chromatography, does achieve kind of the same thing. So this is what it is, separation for identification. When you do that, I'm used to doing it in year 7, but I can't imagine you haven't done it when you were much smaller, with ink and filter paper, and the colours separate. That's separation for identification of the colours. A more sophisticated version is amino acid separation on chromatography paper, which is very similar to filter paper. And then there's also TLC, which is another technique which is not that dissimilar to paper chromatography. So this is why they're listed here. So paper C is paper chromatography, TLC is thin layer chromatography, and GLC is gas liquid chromatography. Do this in school, using in the 6th form. Be a rich school if you did it lower down, because the plates cost money. And GLC is a machine. School side, I've never worked in a school with one. So it's for identification. There is another type of chromatography which is not in A-level courses, called column chromatography. It's the only one that goes past the identification. In column chromatography, you actually can collect enough of the sample to say, I've produced this material and I've separated it from this material. Normally for identification, you just literally get a very small amount in different locations on the paper, on the TLC plate, or coming out of the gas chromatography machine. All three of those work on phases. Phases being the two materials involved in separating your mixture. So there is always in chromatography what's termed a stationary phase, which is one that does exactly that, it doesn't move, and a mobile phase, which does the opposite, which does move. So when you look at paper chromatography, and if you go, I still can't think of it, you will remember doing those ink chromatographies. So the ink is not the stationary or the mobile phase. So the chemicals you're looking to take apart from each other are not the phases that we are talking about. The phases are the inherent parts of it that are either one of the two things you put together and then put your mixture onto it in some way or another. So paper chromatography, the thing that doesn't move is the paper, usually chromatography paper or filter paper if it's really lower down the school. The mobile phase is a solvent. Now lower down the school, year 7, it would have been water. As you get a little bit more sophisticated up the school, if you're doing amino acid chromatography, it will be ethyl ethanoate, ethanoic acid mix, if I remember rightly, or sometimes with butane 1-ol in there as well. So it's just a solvent mixture, and you do that on paper. Now TLC, very similar. It's a plastic plate, and they are somewhere around, I mean they vary in size depending on where you bought them from, but they can be up to 10 centimetres. This is my cat interfering behind the camera, that noise. It's a plastic plate, and they vary in size between 5, 6, 7 centimetres. Sometimes they're like 10 or 15 centimetres, depends how much money you pay. And they are coated with very fine silicon dioxide, so they looks like white coating on it that if you picked at it would powder off, which is what it is. It's a white powder adhered to the plastic backing. So the stationary phase in TLC is silicon dioxide, that very fine coating on the plate, and the mobile phase is again a solvent mixture, and that solvent mixture could be any liquids at all, depends on what works, quite frankly, for what you're trying to do. And so they're very similar in the way they set up. You have a flat piece of paper or plastic plate, and you watch the solvent climb up, and before it gets to the top you take it out, mark it, everything is ready to analyse after that. But we're not here to talk about those two. Those are things you may be familiar with. GLC you will, in school, I can't imagine you'll ever see one, but it's something you need to know. There is also another thing called HPLC, High Performance Liquid Chromatography, which is very similar. Now, in GLC, which is a not massive machine, I mean the ones I've seen are sort of so size, sort of box like that. Yeah. Not an enormous machine, it's not like a mass spectrometer, which is much bigger. And they have a stationary phase. The stationary phase is a high boiling point oil. But it isn't just the oil. That oil is it's a very small amount of it, and it's spread over what's termed an inert solid. An inert solid is obviously something that plays no role in the chromatography separation itself. It literally is there just to have the oil over it. And it just means that instead of packing it with a solid, not a solid would be wrong when it's a liquid, packing it full of liquid, which means it will be hard to get the material through. You just have the liquid, a very thin amount of it over the surface of it's probably like little tiny balls is a way to think of it. And then you have a mobile phase, it's the word inert again, an inert gas. And there are usually two choices, unless you've got a really reactive substance, when I guess you would go for the inertest of inertest things. I'll say that in a second. So, cheapest gas you can use is nitrogen. If nitrogen is if the chemicals react with nitrogen, you might use argon. If you've got really reactive things and you want to separate them, the expensive option is helium. And so they're all inert because they don't react with the substances that you're trying to put in there to separate them apart. You do need to have some idea what the machine is internally looking like. Yeah. So we're going to have a little drawing on the board, which means I'm going to have to wipe this, and we're going to have a little edit. See you in a second. So, a little schematic of it. Obviously it would be completely sealed in a case with some control dials and stuff to make it do what you want to do. But the basic idea is your inert gas goes, it's from a cylinder, one of those big gas cylinders, and goes in, and the journey is obviously down that way because it goes through, and the tube is really quite thin, and it goes around probably goes around more than once, but it's a coil because it's about a metre of tube, but what you don't want is a machine that is like a massive metre long because it's like cumbersome, so they just coil it up on itself. And then it goes up to an electrical detector that detects when this detector is to detect the arrival of chemicals from your mixture. So you don't need to know how it does that in particular detail. And so what you have is a flow of gas through there. You inject, literally with a tiny syringe, you inject the chemical mixture into the inert gas stream as it goes through. But there's a really important thing missing from all of this, because if you're injecting in some solid that has been perhaps dissolved in a solvent, you're injecting a liquid in. It's not going to go through the machine. So the whole of this box represents the fact that it's all done within an oven, so that everything that you inject into it becomes vaporized. That's why in the little table before it said high boiling point oil, because it needs to be quite hot in here to vaporise lots of their, or it's usually organic, it's usually organic chemicals, and they need to be vaporised to work through the GLC. So the whole thing's mounted in an oven, and they run through there and they get detected. Now the whole way it works is like that paper chromatography. In that paper chromatography, some colours go a long way, other colours don't go so far. It's the same idea. Some get through here really quickly by getting through with the carrier gas or the inert gas. Others get caught up on the stationary phase. And so as they go through, they're spending a lot of time interacting with the stationary phase, the oil. They'll take longer to come out. And we are talking minutes here. We aren't talking like poof, 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 done it in a couple of seconds. And it gives rise to, as it goes through, something that interacts well with the carrier gas or the inert gas, gets through quickly, and it has a short retention time. So we are talking the word retention time, which is what the detector gives you. So the output is a series of retention times, and we'll look at what the output looks like in the after the edit when we do it, but I shouldn't be finished with this. So they go through here, things that interact strongly with the inert gas but not with the oil come out quickly with a short retention time. Things that interact more with the oil and therefore less with the inert gas have a longer retention time because they get caught up on the stationary phase and don't move so fast, and they have a longer retention time, maybe 15 minutes rather than 2 or 3 minutes. And that's how you achieve the separation, by them being retained for different amounts of time within the coil that is the key part, with the two phases within the coil, stationary and mobile. We'll have a look at what they look like and a couple of other things, but I'll just get the board ready for that. See you in a second. Here's the other responsible monster for making the noise. The partition coefficient is mentioned in textbooks, but it leads to a retention time, but we don't really get into how that happens. Obviously a bit too complicated, I guess, but this is the partition coefficient. It's an equilibrium constant. It's the concentration of your particular chemical that you're talking about at the time. So if you look at this here, this is 3 chemicals, so each one would have its own partition coefficient, and it would be the concentration of it in the stationary phase against the concentration of it in the mobile phase, and that gives you an equilibrium constant. And the result of, if that is bigger than that, it has a long retention time. If that is bigger than that, it comes out quicker, and the retention time is shorter. That's as much as you need to have. This here is an example of the printout from a GLC machine. It shows that there were 3 chemicals. It shows that if we give them the labels A, B and C, it tells you, and this is the retention time, so no minutes to 15 minutes, so they have different times. These two were obviously fairly similar in retention time, but it does one other thing in a gas chromat, well, GLC printouts, it's called gas chromatograms, that's probably not right, is that there's less A marginally than there is B, and there's a bit more C than there is B, so the actual area underneath, they are quite sharp peaks, so I've drawn them quite wide so you can see them, but they're quite narrow, which means almost the height tells you how much of each chemical has come out of them, or was present in the mixture, more to the point, because it comes out in the detector, but the assumption is that it all gets through. So the peaks tell you that. Now that should ring a little bell, like that's a bit like isotopic abundances when you're looking at mass spectroscopy, because the analysis of it would be the same. The area of the peak is equivalent to the height of the peak in mass spectroscopy, and that's also true for NMR as well, the height of the peak or the area underneath the peak tells you how many atoms you're referring to with that chemical shift. So it's a similar sort of thought process. So more C than B and marginally less A. It will do it's quite good at separating out things. So you can have things that are fairly similar. You could have an E and Z isomer of a chemical. They would not have the same retention time. They would be similar in retention time, no doubt, but they would not be the same. So you would achieve, firstly, identification of the fact that you had both rather than one. Secondly, you would know the relative proportions of the E against the Z. We're going to do one further example and then we're done. See you in a sec. So, quick little question, 3 parts. There's the printout with retention times along the bottom from 0 to 20 of some kind of mixture put through GLC. 3 questions. How many substances? Which is the most abundant? Which are the racemic isomers? Racemic being 2 isomers, optical isomers, equal amounts of both would make it racemic. My cat is now playing with a stone on the floor. This is the other one, the brown one. Please refer to other videos if you wish to see it. And so what I'm going to say to you is I'm going to ask you to pause the video and answer the 3 questions. It won't take you very long. And when you come off, pause. We'll put the answers on. We don't need to spend very long pausing. You just pause the video for me. And now you've had to go at the question. Oh, you haven't done it. I'll pause it again then. Well, you know what I mean. And then here we are. How many substances? 6. A, B, C, all the way through to F. Which is the most abundant? B. Which are the racemic mixture? Now this is, you're going, oh, could be C and D. No, slightly too far apart. E and F. And the reason it's racemic is also they're the same height, because racemic means equal amounts of both of the optical isomers. And they're very close together because that was likely to be what happens with the, in fact you may be struggling to see the 2 things separated out. Right, that's kind of it. I don't think there's any point in having some follow-up questions for you to do on your own because that's all there is to it. Thank you for watching. I'll see you soon.